Now that we have the basic idea of linear systems, let's start to slowly get into solving them. Here's a very, very basic system of equations that we learn how to solve in basic algebra. But let's look at how to solve this. So the first thing we're going to do is multiply the top equation by -2 and add it to the second equation. So like I said, we multiply the top equation by -2 and then we add. We can see the x's cancel. On the left, we're left with a -5y, and on the right, a -10. And for now, I'm going to go ahead and keep this written as 0x minus 5y equal to -10. And the idea is this is going to replace my second equation, so now I have a new system of equations. So here's my new system, the original first equation, and I replace the second equation with this new one. The next thing I'm going to do is actually divide this second equation by -5. So my first equation didn't change, and the second one becomes 0x plus y equal to 2. The last thing I'm going to do is subtract the second equation from the first equation. When I do that, I can see the y's cancel, the left is left with an x, and the right is left with a 3. So now I have two much easier to understand equations. I have x plus 0y equal to 3, and 0x plus y equal to 2. So my solution is 3, 2. And this is a very, very long process here. So we want to try to simplify it. And that is our ultimate goal, is to try to simplify how we did this process. So the way we're going to simplify this is with matrices. So what exactly is a matrix? A matrix is just a rectangular array of numbers. If I know the matrix has m rows and n columns, and our size is m by n, we do the number of rows by the number of columns. We tend to denote matrices by capital letters like A, B, C. And my last piece of notation, the entry in row I and column J of matrix capital A is denoted by lowercase a with subscripts I and J. So once again, just like the size, we do the number of row and then the column number. So let's do an example of this. This right here is how we typically denote a matrix. So it looks like a rectangular block of numbers with these square brackets on the sides. So the first thing I want to know about this matrix is its size. And as I said before, the size is the number of rows times the number of columns. So we can see that there are 1, 2, 3 rows on this matrix, and 1, 2, 3, 4 columns. So this matrix is of size 3 by 4. The next thing I want to know is what's in entry A13. So we start with row 1, that's this top one right here, and column 3. So that would be -1. So A13 is -1. Now let's find A21. So 2 means row 2 and 1 column 1, and that gives us -9. So A21 would be -9. Now that we know about matrices, let's actually look at how I can simplify that system of equations. And I'm going to do this with the idea of the coefficient matrix. So here's the system of equations that I looked at before. The idea of the coefficient matrix is it just deals with the coefficients of x and y, or x1, x2, x3, etc. So it just looks at the actual coefficients in this equation. We can see the first equation, the coefficients of x and y are 1 and 1. For our second equation, the coefficients are 2 and -3. So this would be our coefficient matrix. A couple of things to notice about this. Every row corresponds to a single equation. So this is the coefficients for the first equation. The second row are the coefficients for the second equation. Columns correspond to variables. These were the coefficients of x, and these are the coefficients of y. So we want to make sure the variables for our x are all in the same column, the variables for y are in the same column, the variables for z are in the same column, etc. The next thing we want to look at is going to be the augmented matrix. The augmented matrix is going to be a modified version of the coefficient matrix. So we add the constants to the final column of the coefficient matrix. So let's look at what that looks like. So here's my matrix, or here's my system of equations. We had formed the coefficient matrix previously. But this time we're going to add a column. For the augmented matrix, we tend to draw this vertical line to kind of represent the equal sign in the system of equations. And then on the right, we would have 5 and 0. And so now I have my augmented matrix. We know that we have the coefficients for x in the first column, coefficients for y in the second, and then the constants are in the third and final column. And like I said before, this vertical bar represents the equal sign. The next thing we want to look at is the idea of equivalent systems. Equivalent systems are systems that have the same solution set. As an example, here's the system that we dealt with earlier, and we formed the augmented matrix. And once we solved the linear system, we had two equations. We had 1x plus 0y equal to 3, and 0x plus 1y equal to 2. So there's the augmented matrix for that system. And these would be equivalent because they have the same solution set. They both have the solution 3, 2. And we can see on the right, this one's much easier to figure out what the solution is. 1x plus 0y equal to 3, so x is 3. 0x plus 1y equal to 2, so y is 2. So this is our ultimate goal, is to find an equivalent system that looks like this one on the right, since it's easier to pull out the solution for it. So how can I go about changing a matrix to still have the same solution to make it easier to find the solution? Well, let's go back to actually solving an equation. So when we're solving a system of equations, there are three main operations that we know we can do. The first thing we know we can do is add a multiple of one equation to another. As an example, when I solved my linear system, I multiplied the first equation by 2 and added it to the second. We can multiply an equation by a non-zero constant. This is something else I did whenever I solved my system. I multiplied the second equation by -1/5. And the third one, something that I didn't do but we could have, is to interchange the equations. There's nothing unique about the order we write down the equations in, so you can switch the order at any time. So now that we see that, we want to see how that translates to matrices. So we're going to look at this idea of elementary row operations. And the elementary row operations are essentially how we take these three operations and move them in terms of matrices. The first operation becomes this idea of replacement. We replace one row with the sum of itself and the multiple of another row. So we multiply one row by something and add it to that other row and change this other row. The second thing I can do with operations becomes this idea of scaling. We multiply all entries in a row by a non-zero constant. And finally, we have this idea of interchange. Like I said, there's nothing unique about the order that the equations were written down in, so at any point we can just switch two rows. And that would be equivalent to just switching two equations. So these are our elementary row operations, and these are the things that we can do to create a still equivalent system, so it doesn't actually change any of the solutions to the linear system that we're given.